Okay, the example we worked out last time, even though there was a mistake associated with vertex number 3, I think you have a fairly good idea of how to work out these things numerically, at least by inspection. Now, what I'm going to do today, let me just close the door first. What we're going to do today is I'm going to give you an algorithm for solving the dual problem. And then we're going to find the weak duality relationship and the strong duality relationship between the two problems. And then we'll prove these. And if time permits, maybe we'll go also into the business of how to compute beta ij values, which are the crucial numbers that we've been working with. Okay, so let's first state the dual opt. I already gave you an algorithm for solving the primal problem, the primal p-center problem. If you don't recall where it was, it was maybe 2 or 3 lectures ago, called primopt, coming from primal optimization. Okay? Now, the dual opt. If the p-center optimal objective value is alpha, which is the maximum of the Fi0 values, and suppose the maximizing index is S, if this is the situation, then we take the optimal solution, the dual solution, K star, to be any threat for which the cardinality of the threat is p plus 1, provided that the index S is in K star. So step 1 says you're going to choose any subset of the vertex set or the set of indices of the vertices such that the set you've chosen has p plus 1 indices in it. The number 2 requirement is the index S, which supplies the value of alpha, should be in that set. So as long as you include S in the set, you will be solving the dual optimization problem. In the remaining case, the optimal objective value of the primal ZP is greater than alpha. So this, of course, assumes that you have a knowledge of ZP. So you must have solved the p-center problem in some way, or somebody must have told you what the value is. Okay, so in this case, we compute a number which I call ZP prime, which is the largest value in the set R, which includes all beta ij's, which is less than ZP. So you know ZP, you'll look into the list R and you truncate the portion of the list which has all those beta ij's greater or equal zp. So those are removed. Of the remaining ones, you pick the beta ij value, which is, of course, smaller than zp, but which is largest among such numbers. Okay? Then choose any value z such that z is strictly between zp prime and zp. Now, because zp prime is strictly less than zp, by definition, there's a choice for z. Okay? So whenever you do something, you make sure that you are able to do it, actually. Step 2. Use the algorithm cover to solve the covering problem C of z. I gave you the definition of C of z before, so I'll go through that one more time. But nevertheless, we'll put the covering problem C of z in such a way that it will be actually solvable by the algorithm cover. Okay? And obtain an output. The output of the cover consists of two parts. One part is the x part, the other part is the u part. Okay? Obtain an output, say x and u. X is the set of centers that solves the problem. U is the set of vertex indices that supply the tight strings at the times when you located the centers. Do you remember what I'm talking about? Well, I'll go through that after we finish the algorithm. So, obtain an output x and u with cardinality of x and u being equal, and say some number q, some integer q. Since the number z you picked is less than zp, we must have the cardinality of x greater or equal p plus 1. Why is that true? Think about it. So, in this case, we know that the set U consists of at least p plus 1 or possibly more vertex indices. So we take K star to be any subset of this set U consisting of some p plus 1 indices. Okay? So take K star to be any p plus 1 members of U. Of course, if U contains exactly p plus 1, then you have only one choice. If it has more than p plus 1, you've got alternate choices. But it doesn't matter which one you pick. 3. This is the conclusion step. However, you constructed K star either in step 1 or in step 2, g of K star is in fact equal to Zp, and K star solves the dual of the p-center problem. Is that the name I gave? Because sometimes I change these names. Okay, that was the name I have given. Okay. All right, I'll of course, we'll prove this, but first let's understand what we're doing. To understand what we're doing, well, step one, I guess that's pretty straightforward. If it turns out that your optimal p-center solution value happens to be supplied by some vertex S with the loss function evaluated at 0, that means you have to have one center on top of vertex S. You cannot do any better than that. So in that case, it doesn't matter how you choose your p plus 1 vertices as long as you include that particular critical vertex in the set. Okay? And any such solution that includes S in it and has the remaining members coming from the vertex set will be an optimal solution to the dual problem. In the remaining case, we solve the covering problem. First, let's remember what the covering problem was. The covering problem, I stated it in short notation. Well, the optimal objective is Q of Z. This is for fixed Z. You're minimizing the number of points to do the job. And the job to be done is the loss measure, f of x, is less than or equal to z. And what else? The distance of x to each vertex vj is less than or equal to uj. And of course, x is some point set in T. Okay, now how do you solve this using cover? Well, what you need to notice is that this particular constraint is equivalent to having each fj evaluated at dx vj being less than or equal to z. So that portion is that one. This portion, you can still include that. So equivalent problem is the following. I'm not going to change the name because they are equivalent. You're still minimizing the cardinality subject to. Now, this constraint together with that constraint was equivalent to each dx vj being less than or equal to ej of z. Where, by definition, ej of z is equal to fj inverse evaluated at minimum of, minimum of either z or fj of uj. Okay, and this minimum or this function will output either uj or fj inverse of z. It will output fj inverse of z if z is the minimizer here. And it will output the other one if fj uj is the smaller one. I included equality in both cases because when they are equal, they give the same value. It doesn't matter. Of course, there's one question you should always ask. Is Z in the domain of definition of Fj of inverse? It will be under what condition? If Z is greater or equal Fj of 0, right? So how do I know that this will work out? Well, of course...
ZP more than alpha.
Exactly. Yeah. That's already implicit because we're using Z to permit feasible solutions. That will be ensured. Okay? Okay. So when you use the covering algorithm, cover solves the problem C of Z by using string lengths defined by Ej of Z. Okay? I should also refresh your memory on one thing. The Ej of Z, well, this problem is equivalent to this problem provided that Z is greater or equal alpha. We've actually worked this out before. So you should add that Z being greater or equal alpha actually ensures, as Barış just said, that Z is in the domain of definition of each Fj inverse. Okay? Okay, so at least we know how to use the covering algorithm to solve this problem. And now that you are crystal clear on how to use the algorithm, we can go ahead and start proving the duality theorems. As related to the P-center problem and the dual of the P-center problem. Assume there's a feasible P-center solution to the P-center problem. Because of the upper bounds on the distances, we may or may not have a feasible solution. I just assume there's a feasible solution. So under this assumption, if X is feasible to the P-center problem, and set K being feasible to the dual of the P-center problem, we have the objective value of the maximization problem. You're trying to maximize the G of K value in the dual problem. In the other one, you're minimizing the f of x value. So it turns out that the objective value for the maximization is bounded above by the objective value of the minimization. That's the typical situation with any duality theorem. Okay? The feasibility of the solution X to the primal problem PC implies X is in the feasible set. In other words, it satisfies the distance constraints provided by the UJs. And the feasibility of K to the dual of the P-center problem implies K is in CP plus 1. What was the definition of CP plus 1? C sub Q for any Q is the set of all vertex sets that has at least Q or more elements in it. Okay? Rather than actually working with vertices, I refer to the vertex indices, but whenever I say vertex, that means actually it's the index I'm talking about. Okay? All right, so K has P plus 1 or more vertex indices in it. That's what that means. Okay? Now we have either G of K being equal to alpha K or G of K being greater than alpha K. Why is that? Because G of K is defined to be the maximum of two numbers, alpha K and beta K. So these are the only possibilities for that reason. If G of K equals alpha of K, then G of K is, well, by assumption it's equal to alpha K. Alpha K is less than or equal to alpha. What is alpha and what is alpha? What is alpha K? Alpha K is the maximum Fj0 value restricted to set K. Alpha is the maximum Fj0 value for the entire set of vertex indices. Okay? So, alpha is computed relative to a larger set, which includes K as a subset. For that reason, the maximum of the smaller set will be bounded above by the maximum of the larger set. Okay? All right, so that one is due to K being subset of J. That's the reason. Now this guy is less than or equal to ZP. Why is that true? It's quite true because ZP is supplied by some optimum solution, but the optimum solution is defined by the maximum loss. The losses are Fj values evaluated at distances. Those distances are always non-negative. So any loss measure can never be smaller than the maximum you get here. Okay? That's the reason. All right, we've actually done these things, but I'm just sort of trying to make you have them all ingrained here, because if you keep repeating sometimes, it just stays there even better. Okay, so ZP, and this I know is ZP is less than or equal to f of x. Why? Obviously, because x is any feasible solution, so it must have at least as large a value as the optimum value. So we have a series of inequalities here, and of course I already got what I wanted. G of K is less than or equal to f of x. That's what I wanted. So in this case, I'm done for this case. Let's continue with the remaining case. Then, in this case, g of k, because it's the maximum of alpha k and beta k, in this case it's obviously defined by beta of k, which we know is greater than alpha k. Since the feasible solution we have on hand, x has p points in it, x is, by assumption, feasible to p-centered problem, so it has p points in it. And since k has p plus 1 or more points, we've got this strict inequality, which means at least 2 vertices in, or whose indices are in K, are jointly covered or served by a single center in X. So all we are saying is, because the number of vertices are more than the number of centers you have available, then some 2 of them must be served jointly by a single center. Hence, for some x in the set under consideration, we have for some vertex indices I equals S and T both belonging to K, so, and S being different from K. So we have some 2 vertex indices, S and T, and some X, which serves both of them, which means distance between X and VI, where I equals either S or T, is the actual closest distance of the set X to VI, because X is the serving vertex, which we know is feasible, which is less or equal to UI. Accordingly, of course, the S1 set relative to S and T is non-empty, which means the beta value is finite. First, I'm establishing the finiteness of beta ST. Does everybody follow what I'm doing? I'm not, well, what we're doing is, first we concluded that there should be some 2 members of K that must be jointly served by a single point. So there is a single point X, in big X, and some 2 distinct vertices S and T, where the closest center from either S or T to capital X is defined by small x. And you are feasible. Why are you feasible? Because capital X is a feasible solution by assumption. For that reason, the distance constraints are satisfied, which means that this set is non-empty. This set is simply the set of feasible solutions to the one-center problem with S and T under consideration, all other vertices being ignored. Okay? So for that reason, there's a feasible solution to the distance constraint with S and T. And when there's a feasible solution, the beta ST, which is the minimizing value of the one-center problem relative to S and T, has to be finite. It will be infinite only if there is no feasible solution. Okay. Also, our loss function fi dxvi is the same as fi capital D capital X vi, which we know is less than or equal to f of x. This inequality is true for I equals S and T. Now, when I equals S and T, the first equality is obvious because of the above equality. Okay? Small d is replaced by capital D. And this fi is one of the loss functions in the computation of f of x or in the definition of f of x. So f of x is certainly greater or equal each of the possible fi dx vi values, or each of the loss values. Okay, so we've got that. It follows then g of k, which is by assumption defined by beta of k, is less than or equal to beta st. Why is that true? Because beta of k is the minimum of the beta ij values where I and j come from k. Okay? And because of that, beta st is just one of those beta values, so it will be less or equal to that. So this is simply from the definition of k. Definition of beta of k. And beta st is, I'm continuing with this, is less than or equal to the maximum of fs of dx vs and ft of dx vt. Why is that one true, this inequality? Because of the definition of beta st. Beta st is the smallest value. What is the definition of beta st? Remember, beta st is the minimum r or z, whatever you want to call it. Let's make it lambda. Minimum lambda subject to fi dx vi. Let me use y here because x is a fixed point right now. Okay, dy vi less than or equal to lambda for I equals s or t, and dy vi less than or equal to ui, again for I equals s or t, with y being a point in t. It's the one-center solution value for s and t. So here, when you take y to be x, where x is the particular x that I have under consideration, then, of course, everything is satisfied here. And so the loss values with y being replaced by x's will certainly be satisfied with beta ij here, because beta ij is, or beta st is beta st here. Beta st is the smallest value. Forget the minimization. When you have the smallest value, when you insert that value into your constraints, everything should be feasible, because that's the definition of being optimal. It's the smallest number you can get without jeopardizing feasibility. Okay, so beta st will certainly satisfy these inequalities, and for that reason, beta st, why do I have this reversed now? Sorry, yeah, that's the smallest feasible value, but here x is some point. So, sorry, we can't do this. Yeah, I can't do this. Sorry about that. X is some feasible point because I already showed that x is feasible when I equals s and t, okay? So, x is some feasible solution, so the maximum loss defined by x is greater or equal the smallest loss you can get, okay? That's the reason.
Why you can't do it?
Pardon?
Why you can't do this replacement?
Whether or not x is optimal, we don't know. That's why we can't do it. If we know x is optimal, then it will be feasible. But if x is not optimal, of course, the inequality will be reversed. Okay, so sorry for the confusion. Yeah.
We know BST equal to the maximum of...
Where are you?
The last one.
This one?
I think that will be equality. Am I right?
Well, of course, but first we're using the primitive facts to actually get our well-justified inequalities. Then finally we'll get... I don't need an equality here. I'm trying to prove that this inequality holds. That's what I'm after, okay? So let's not shoot for anything more than what we're trying to prove. Don't ever, whenever trying to prove something, don't go for something more. If you go for something more, then write your statement at the beginning accordingly. But these things come in pieces, okay? All right, right now, all I can say is beta st is the smallest feasible objective value for the one-centered problem with two vertices. For that reason, whenever you have a feasible point x, the loss, that's the objective value for that point, will be greater or equal to smallest value you can get. It's the definition of that, of beta st. Now tell me why you thought it was equality, just momentarily. Yeah.
So this problem, lambda will be equal to the maximum.
Yeah, I'm going to get an optimal solution, say x bar.
Yes.
But I don't know if that x bar happens to coincide with the x I have under consideration. I never know that. Unless, of course, you have other machinery to justify that. Okay? That's why that would be dangerous to have equality here. Okay? All right. Okay, so from here, this one, if I just continue over here, it's going to be the maximum of fs capital dx vs and ft capital dx vt. This equality is well justified because over here I've already shown that, okay? Or argued for that. And this is less than or equal to f of x. Because again, f of x in its definition includes all of these loss functions. And so it should be at least as large as each one of those loss functions. Okay? So, am I done? I should be. I begin with g of k, then through a series of inequalities, I've got less than or equal to f of x. That's it. That's the end of your proof. Okay. Okay, next I'm going to give you the strong duality theorem, but we're just about out of time, so let's take a 10-minute break and then we'll be working on the strong duality.